VLPSos here. This is a video lesson for Python programming, hold movement. This lesson began with the code file for step movement. We're going to look at what we accomplished in the step movement lesson and then modify it for a different kind of a movement algorithm. Our step movement, we'll run it to observe that previously we had a green square that's an instance of an object class move around by the pressing of arrow keys. One key press, one jump or step of movement. We also implemented the ASDW keys in order to do the same kind of movement, but the algorithm to process and accomplish what the user sees is a little bit different. So two different techniques for the same kind of movement. We also implemented the holding down of the shift key in order to get a bigger amount or a larger step when we press those directional keys. Let's take a look at the code that accomplished this. We had a class called object to create an instance that the user could see the green square. The attributes were an X position, a Y position. Step was the number of pixels that one key press would change the position. It's the amount that it would change the positions by in pixels. And size was used simply for the width and height of the square that the user sees. We had a dictionary, have a dictionary called things, in which we created one instance of what we're using to move around. We have two different algorithms in our frame loop. One under the comment based on descriptive string values, and one algorithm under the comment based on booleans. So string values and booleans were the two different ways that we implemented this kind of motion. We also have in the event queue, where we are looking for a place in computer memory when we're processing our frame loop that the user might have given us some input. This is where we react to that input from the user. We implemented under the condition event type 2 or 768, which are the numbers for the pressing of a key down, which is a different event type than the release of a key or any kind of mouse buttons or mouse motions. Under that condition, which is this code block to process different keys that we might have pressed down, we check to see that the 4 direction keys, literally the arrows left, right, up, and down, which have numbers associated with them, when we checked whether we had a key down event for any of those 4 specific keys, we had then the assignment of a variable called takeStep to be a string, which then was the string itself was a description of the kind of movement that we wanted to implement. So the pressing of the 4 keys assigned to a variable called takeStep a string. And the algorithm in our frame loop then responded on the value of takeStep. If takeStep was anything at all, on condition of takeStep being something other than no value, it would then check the specific value, whether it was left, right, up, or down, and then make the appropriate change to the position of the object by adding the step amount, in this case 10 pixels, in one of the 4 directions. Part of the code block was then to reassign, once this happened once, takeStep to be none. None being the word for no value for this variable. Only a key press would assign a value, a string value, to the variable, and if the variable had a string value, it would react to it once and then make it have no value again. So we'd have one motion per one key press. Well, we accomplished the same style of movement with different keys in a different way. We implemented on the event type of a key press 4 additional keys, A, D, S, and W, but in this case, instead of assigning a variable takeStep to be a string, we had 4 different variables, one for each of the 4 directions. and we assign those variables the Boolean value true. For example, the pressing of the D key would assign the variable step right to be true. And if any of those 4 Boolean variables were true, then we would react to their values by changing the position based on which one was true. And in fact, since this code block has no elifs, it is possible to get 2 different motions or more in one iteration of our frame loop. So in this case, if we press the D key, then the step right Boolean would be assigned to be true in our event queue. And here it would check that condition. If it was true, then we would immediately reassign that Boolean to be false to get that 1 key press per 1 change in position. And then it would also do the math, the appropriate math, to change the position of the instance that's being drawn for the user. We also implemented a big step Boolean, a Boolean called big step, in order to change the amount or the stride in this case that would change the position. So if big step was true, then we implemented this thing called stride, which would triple the step attribute. And if big step was false, then stride would simply be equal to the step attribute. So we change our position based on stride to get 2 different stride values, a big one, which is triple, or the regular one, which is what we set when we created our instance. Now we're going to implement the movement style where if we press a key, then we'll see continuous movement in the direction that we pressed. And the releasing of the key will stop that continuous motion. So instead of 1 key press and release being 1 step, we're going to hold the key down to affect the motion and get it to stop by releasing the key. Now we've already coded for that style with the shift key. And here's how we accomplish that. The key down event is a distinct type. Key up is a distinct type. This code block under the condition of event type 2 or 768 are all of the keys that react to a key down event. We have a different code block to implement key up events. The pressing down of A, D, S, and W previously assigned a Boolean to be true, just like the pressing down of the left shift key assigned big step to be true. In the key up code block, only the left shift key was included, so that if a key up event happened, and if it was specifically the left shift key that got released, then it reassigned that big step Boolean to be false. In other words, if we press the left shift key down, big step is true. And it continues to be true until we release that key and a key up event has been detected, and that left shift key then makes the big step false. We want to do that for A, D, S, and W as well. I'm going to highlight this code block and copy it, and then paste that same code block under the key up condition. And instead of detecting a key up and assigning the Boolean, then the appropriate key, to be true, I'm going to turn it back false, a reassignment, just like the shift key. Now the keys left shift, A, D, S, and W have this hold down effect, where if we push it down, push the key down, the Boolean is true, and the only way to get it to be false is to release that specific key. Which means that in my movement algorithm, we're going to take out the reassignment of those Booleans to become false, because the way they're becoming false is based on a key release and not immediately after we test the condition of them being true. Let's see what kind of effect we get immediately. The arrow keys are still implemented for step movement. Now if I press the D key, I'm going to expect rightward movement, and I get it. But I pressed it briefly and I released it, and the object shot off to the right very quickly. The reason for this is because the Boolean, when I pressed right, I'm going to change the X position by my stride amount. So step right was made true when I pressed the D key down, and it didn't become false until I released the key. Now I released it quite quickly, but in the amount of time that the key was pressed down, there might have been hundreds of frames that were processed. And every single frame that was processed changed the X position by the stride amount, which is 10 pixels. So that was 10 pixels per frame for all of the frames that the key was held down. It was enough to have it shoot off so fast I couldn't see it. And in fact, I don't think I could press the key fast enough to get the object to not move so much that it's going to be off the screen. What I need to do is I need to change the stride amount. But if I do change the stride amount, then I might affect the other implementation of the step movement. So I'm going to introduce a new attribute to my object called speed. And I'm going to set it to a very low amount, 0.1. This attribute speed then is how I'm going to change the location of my object. Instead of stride, I'm going to change it by this much lower amount, speed. Each frame. Now I've abandoned the use of stride for the moment, so my big step Boolean or the left shift key is not going to affect anything just yet. When I hold a key down, I'm not changing by stride or 10 pixels. I'm changing by speed, which is set to be 0.1 every frame. I still have the arrow keys being the step movement. Now I'm going to press the D key down and I get a continuous movement, and when I release the D key it stops. So I can see the effect of that Boolean true when down, turn back false when up. And I can do that in each direction. And in fact, because my directions are separate conditions, then I can press two keys at once and process both motions, which will then allow the user to see the oblique movement on the screen. Every frame, I'm changing, based on a key press, the position of my object. I'm changing it by a Boolean amount. We can't locate an object on a pixel matrix by fractions of pixels. So what I did in the drawing of the rectangle, which the user sees as a square on the screen, I put my positions into the int function. Because I'm changing it by fractional amounts, my position values, the attributes that I use to locate where it's being drawn, are going to be float amounts. We can't put things at fractions of pixels. And I can show that by taking one of my position values out of the integer function to demonstrate that if I'm moving around, and if it's trying to locate something in a pixel matrix as a fraction of a pixel, it doesn't break the program, but it does send this warning that there is an implicit conversion to integers. because we tried to locate something at a fraction of a pixel. So the warning is reminding us to get in the habit of putting our things, the variables that we use to be positions, into the integer function at the moment that we're using them as pixel locations. Doing that allows us to change our position mathematically by fraction amounts. We want our speed to be something as small as 0.1 because a 0.1 pixel change per frame is a good speed or a good math for the human eye to be able to track the motion at a reasonable speed. But there's something else that we want to do to make this speed be universal or be consistent on different computers. Even though the position changes by the speed attribute, it's also changing by how fast the frame loop can process. The faster the frame loop processes, the more that will add or subtract to these positions. So we're going to make use of time. We've included it in our stub. We created a clock instance that we called watch. At the beginning of the frame loop, we assign this variable to be the tick function on our watch. So timing now is the value in milliseconds of how long it took to process the frame loop. Timing is the amount of milliseconds since the last call to tick on our watch. So if we multiply by timing, then we are tying real-world time to the math that changes our position. If our CPU runs quickly, then the value of timing is low. And so multiplying by timing will have a small effect on the change of the position. If our CPU is processing slowly, then the value of timing is going to be greater because it took more time to process the frame. So multiplying by timing will have a greater effect on the change of position. Now this is proportional, the way that this math works out. That means that if we're running a very fast computer and timing is small because we're processing more frames per second, then every single frame will change the position less. If we have a computer that is running very slow, then timing will be great and every frame will change the position by more than a faster computer. This is proportional so that it works out. If we run our code on any computer, then the actual motion of the object will be consistent on different computers with different CPU speeds. We want to multiply by timing when it's changing our position. Sometimes that means that we would need to increase our speed attribute in order to, or decrease our speed attribute in order to compensate for the fact that we are now multiplying by an integer. But our frames are processing so quickly that the value of timing might be as low as 1 and therefore have no effect, or we wouldn't be able to see the effect or see the difference between not multiplying it. We're going to implement big step. It's not working now because we abandoned this use of stride. We're going to create another variable called sprint factor. Sprint factor is going to get a value based on whether big step is true or false. And big step is true when we're holding the left shift key down and false when we release it. Now, if we release the shift key, if we turn off big step, then sprint factor is going to be 1. And if big step is true, then sprint factor is going to be 2.5. We're going to use these numbers as factors, meaning we're going to multiply the math that changes our position by sprint factor. The value of sprint factor being 1 will not change this math. In other words, when we do not wish to take a big step, when we want our motion to be normal, just the speed, then the value of sprint factor is 1, which means that there's no mathematical change. Multiplying by 1 doesn't change the value of something. But when we hold the shift key down and big step is true, our sprint factor is 2.5. So multiplying by this factor means that it's going to be 250% of what it would be otherwise. It's going to be faster, change in position. Now I hold my keys down and release, and if I hold the key down as well as the shift, I get a faster motion, and I can see the change by holding shift and releasing it. Okay, now you. You have seen how to code for continuous movement by holding down a key and basing the animation on real world time by using an instance of clock. You have also seen more evidence that using Boolean values in the event queue code block is a very practical way to code. Use this code file as a stub and add an effect. When the left mouse button is held down on the screen, the square object moves gradually towards the mouse cursor. If the mouse button is released, the movement stops. It should be possible to move the mouse around while the button is down and have the object follow the mouse cursor. In other words, you're going to, under the code block of mouse button down, implement or affect, I would recommend, Booleans that, when true, determine where the object is relative to the mouse location, and then turn on the appropriate Boolean to get the motion to move towards the mouse. So you're going to detect mouse buttons being pressed. If they are, write an algorithm that simply finds the position of the mouse cursor relative to the object, whether it's to the right, left, up, or down, or any combination. And then based on what position combination they are relative to each other, turn the Booleans on that would then affect the motion to get the object to move towards the mouse. Have fun.